All right, hello everyone. It's time now, so we can do a quick intro. I hope everybody can hear me fine. My name is Sushil, and I'm with Julia Computing. I'll be your host for this today's micro training. Uh, our senior data scientist Deepak Suresh will be the presenter for this training today. We hope to make it interactive. So the best approach is during the presentation, if you have any questions, feel free to type it in the chat box, and then end of the presentation we'll take the questions one by one. We'll give a couple of more minutes to the other folks who have not joined yet, and then we'll get started. I think we can get started now. So a quick, you know, intro on Julia Computing, who we are and what we do. So the company is founded by the language creators, and the whole idea of Julia Computing being in picture was when the language started getting recognition. Enterprises and organizations, they started coming up asking for commercial offerings in terms of support, in terms of products, in terms of solutions, services, trainings, and that's how the company came into existence. It it's founded in 2015. We have our presence globally, but when it comes to official presence, it's in Boston, New York, London, and Bangalore. In terms of our offering, Julia Pro is a distribution, so it's a free of cost product available for seamless development. The product comes with Atom based Juno ID, inbuilt profiler, debugger, compiler, etc. Then there is Julia Team. Primarily, the product is used for enterprise governance, package management. It comes with a list of features, and primarily it makes Julia work seamlessly behind the enterprise firewall. So several restrictions, from running Julia into production, the restrictions which developers see at enterprise level. Julia team, works as a right solution to overcome those issues. Julia Run is for deployment and scalability. So when you build a Julia application and when you have to deploy it, on a number of nodes or on a cluster of CPUs or GPU, this product, saves time and effort for you. It makes, your whole scaling pretty easy, with a single click deployment and several other features, a bit of automation features as well. Julia Shore is our support and indemnification offering. So, developers who are using Julia out there and they see a need of any kind of enterprise support, standard support, production support, ad hoc support, we are here to help. And Julia Shore is our offering which covers those. Pumas is our product which is used by life sciences, pharmaceutical industry, and primarily the product is used for pharmaceutical modeling and simulations, be it your NLME, PKPD, modeling PBPK, your B, IVIVC, and such stuff. So even QSP, the product is used for those. So QSP is done in Julia, but Pumas is primarily a PKPD, PBPK, and NLME, NCA offering product. That's pretty much about it. Without taking much time, I'll request our presenter Deepak to take over from here.
Yep. Suresh.
Yeah, just a second.
Yeah.
You are the host now. Go ahead.
All right. Okay. I'll share my screen. You can hear me, right?
Yeah, go ahead, please.
Yeah. So you can see my presentation now.
Yes, I can. Hope everybody can. So
Yeah.
we can go ahead.
Yes. So
attendees, whoever cannot see the screen or has issues with the audio, you can ping in the chat box. I see a few people see people have pinged. Yes. So we can go ahead.
Going. Yeah. All right. Yeah. Welcome to this micro training session on building and deploying a language model in Julia. So we will be building a language model in Flux. Flux is Julia's deep learning library, and we will be using that to build the model. So the goal over here is to build a language model that predicts the next word in a text sequence. So given a sequence of words, the model will predict the word that comes after the sequence. And language models are used widely in products like Google Assistant, Siri, Amazon's Alexa, and all. So this model that we are going to implement is actually a predecessor to Julia's model. So at that point, there were mainly two different approaches in deep learning. And those two approaches were based on the data, the structure of the data that was fed to the network. So one approach is ConNets, which process data with spatial structure, that is images. And then when you have when you're talking about data with temporal structure, that is sequences, you have RNNs and LSTM. But one drawback is that they don't make use of an external memory to which they can read and write, and that is really useful when you want to build question answering models based on set of facts. So when you want to answer a question based on a lot of facts or story, you would want to access your word sequence in random order, or your knowledge sequence in random order. And the problem is long-term dependency. So So the end-to-end memory networks, this came out of Facebook AI research lab, and in this model, there is an external memory to which you read and write from. So unlike RNN or LSTM models, where you feed the model all data, and then once it's fed to the model doesn't have any access to the input data. So unlike those models over here, the model actually keeps track of the input that is fed to it, and then writes and manipulates that data set. So 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 these models deal with a, let's say, a discrete set of inputs that are stored in the memory. Then uh, for a language model, you would take the next word, right? So, or for a question answering model, you would have a query vector. So the model also takes a query vector, and based on the data that it has, it generates an output or an answer. So, so these models can actually be seen as a generalization of RNN models. So that in a particular setting, you will see that the memory networks work just like an RNN network. So, so so the model writes all the input. Let's say you give it a set of sentences. It writes all the inputs to your memory up to a fixed buffer size. So this buffer size is called memory size. So you give it let's say 100 words, and then over there you restrict the sentence size to 40, and that 40 is your memory size over there. And then the model finds a continuous representation between the input and the query vector. So like I said before, the query vector in a language model is also always going to be the a constant, because it's what's the next word. So so let's take a look at the model architecture. Let's say these can be words, sentences like the dog jumped over the and then that is the input that comes to the model. So the model has an embedding matrix A, which embeds each of the words in the sequence into the memory into the memory buffer. So the embedding matrix A will be of dimension the vocab size cross embedding dimension. And then you also have the query vector coming in. So for language model, like I said, because the query is always going to be same, you need not have any embedding over here over embedding matrix B, because you can always feed in a constant array over there. So this is just like the initial hidden state that you pass to your RNNs. So so this embedding matrix A calculates the input representation. Similarly, we also need an output representation. So output representation is calculated in the same way by an embedding matrix C. Now you may ask, why do we need two representations for the same set of sentences? So the thing is that if you train a model, you will notice that when input and output representations are decoupled, the model learns better. So otherwise there will be a lot of instability. So, so the way this model works is, first, now that you have your input sequences stored inside your memory, the model will do inner product between the query vector and the memory embeddings. And after that, it does a softmax over those inner products to calculate a probability weights. So you have M1 to Mn memory over here, and then this first initial process will result in probability P1 to Pn. So those are your probability weights. And then in the next step, it calculates the output vector. The output vector is calculated by doing a weighted sum between Ci and Ci. So it'll be C1 times P1 plus all the way to Cn times Pn. And uh, and the final output would be calculate will be a sum of your initial query vector and the output from the output from here. So this is then passed through W matrix. So what the W matrix does is, so at this point, what you have is an embedding dimension. So what the W matrix does is, it has a dimension embedding cross the vocabulary size. So it maps the embedding vector back into the vocabulary space. And if you do a softmax over that output, you will be able to predict an answer. You will be able to predict a word as the final output. So this is actually just a single layer. You can see that it's just one hop over the entire model. So if you want better representation power, you will have to do multiple hops. For that, you just have to stack multiple layers one on top of the other. So in this case, notice that if all of your A matrices are same, and if all of your C matrices are same, what I mean is, if A1 equals A2 equals A3, and then C1 equals C2 equals C3, you'll notice that this is just your classic RNN. So that's why memory networks are generalizations of RNNs. So I'll walk you through an implementation of this in Julia. Let me just open up my editor. So now you can see my editor, right? Uh, okay, thanks. Yeah, so we will be building this with Flux, which is Julia's deep learning library. And for Flux, the gradient calculations are done by the Cybert package, which is an automatic differentiation package. That will be the backend that we'll be using. And then BSON is just a serialization that you can use to save your models. Julia actually provides multiple serializations like JLD2, BSON, etc. But I'll be using just this one. And also you have a lot of helpful functions in the NNLive package. So one thing I'm going to use over here is log softmax. So softmax is kind of numerically unstable compared to log softmax. So I'll be using log softmax over here. And there are three helper functions that we will go through. The first one is the function that creates the training data. So so like we said before, the initial query vector is constant always. So x here is your input query vector, and we fill it with a constant value. And another thing is, since for a sequence of words or for a sentence, the order of words are important. You can't mix them up. So we need a time encoding. So to keep track of which word comes up first, which word comes second, and so on. And then there is the target metrics, and then there is the context metrics. And it's in the context metrics that we hold the input sentences, and the target metrics will be the word that should follow the sequence. And then you have the trainables, the trainables method. So what this method does is, since I'm going to define my model as a custom Julia object, so it fetches all the trainable variables from my model. And I'm also going to do gradient clipping while training, just so that my gradient don't explode. So one nice thing about Julia is that since all these packages are written entirely in Julia, you can drop down to any level of abstraction you want. So you can, the internals are easily exposed. So you can, over here, I'm taking a gradient of a particular parameter and then setting it to a particular value. So you can do all kinds of manipulations because all of these internals are easily exposed. Now we will talk about defining the model. So this is my struct memory, which is the model, which holds the model parameters. So it has an EDIM, which is embedding dimension, Then there is a linear dimension part, because sometimes you may choose to apply a nonlinear operator like ReLU on the embeddings. But empirically, it has been shown that you need not apply your ReLU operator to the entire embedding vector. You can apply it to a part of it. So let's say your embedding dimension has size 40, and you're going to set your linear dimension to size 20. You'll be applying ReLU only to first 20 entries in the embedding vector. You're not going to touch the last 20 vectors, the 20 entries in the vector. And then there is in hops. So this is the multiple hops that we're talking about in the previous slide. And then you have the memory size. This is the buffer size. This determines the number of words that the memory can hold. And then you have the initial hidden state. So this is really similar to the hidden state that you have in RNNs. And then you have your embedding matrices A and C that we talked about. And then we also have TA and TC. So like I said before, we need to keep track of the order of the words. So these matrices help us do that. And then there's a final W matrix which transforms the final output to the vocabulary space. So in order to create these embeddings, so notice that these embeddings are just your regular Julia arrays. It's unlike in TensorFlow or PyTorch, you don't need a specific embedding layer, because Flux weaves seamlessly into the base Julia primitives. So you can just use base Julia arrays as embeddings. So we create embeddings, embedding matrices A, C, TA, TC, and W. So that completes creation of the memory model part. So now let's see how it generates a prediction. So given a hidden vector, which is also the input query vector, and then it's also given a context. Context here is the sequence of words. So we are trying to predict the word that comes after the sequence. So first, the sequence of words are embedded. You calculate the embedding for the sequence of words using the A matrix, and also you calculate the time embeddings, and then you add them up to arrive at the final input representation. So you do the exact same thing for the output representation. You need uh, uh, input and output representations for the same context vectors. Now, like we said before, so the model first calculates inner product between your input query and the context vectors. So A in is actually the input representation of the context, and this is the query vector that we got from above. So it calculates that inner product. Then we do softmax. So like I said before, I'm doing log softmax and then doing an exponential. This is just for numerical stability. It helps during the training part. You can use softmax and avoid the exponentiation and all, but it can go unstable during training. And then you do a weighted product of the output representation and your probability. And the final, the output vector will be your initial hidden query vector added to the output from the output representation. And there is one more step over here. Like we talked about linear part of the embedding and non-linear part. So if you set the linear and linear dimension the same as the embedding dimension, you won't have to do anything. The final output is the same as the sum that we calculated above. If the linear part is 0, then you apply a ReLU all through the final embedding. Or you can also do something like this, where you apply ReLU to only a part of it, part of the output embedding. So this is actually what the authors have done in the paper. So when I train my model, this is what I did. And then you can call this so this the entire thing is run for a certain number of hops over the network. So I actually use 3 hops over the network. So you need actually more than one to get really good representation. And so that's how one input is processed. Now that we have that function ready, we can actually run a batch of sequences through it. And so so that function actually returns the final hidden state, final output. And like we said before, there's a W matrix which transforms the embeddings to the final vocabulary. So this multiplication does that. And then the loss over here is a logic cross entropy between the targets and the output after multiplying the W matrix. So we accumulate the cost over here, and then there is a train method uh, uh, which runs all these methods above. So we can define the optimizer, which I've used the base gradient descent and the trainable parameters. So the get trainable function will give you all the trainable variables in the model, and then you define those as your parameters. And inside the loop, you keep sampling from your data set. This is actually the Pentree Bank dataset that I've used over here. And then comes the zygote part. So over here, you can see a gradient method being called. This gradient method is from zygote, which is Julia's automatic differentiation package. And it differentiates this run batch function. So we talked about how the run batch accumulates costs over here. So we want zygote to differentiate that cost with respect to each parameter. So we have our parameters defined here, and zygote is going to give you the gradients of the cost with respect to each parameter. And then I also do gradient clipping after that. So just so that it doesn't explode. And after that, we apply we update our parameters with gradients. So you can continue that, and you can use serialization like bson to save your model. So I have done all this, and I have a trained model with me. So I'll just walk you through how to deploy a trained model in Julia. So when it comes to deploying or hosting APIs, Julia offers multiple options. So you can use mux.jl, http.jl is another one, and genie.jl is also a popular one. So over here I'm using mux, and so uh, and we had saved our model as a JSON file. So you will have to load it back, and then we need a helper function over here. So what this helper function will do is, let's say you are going to call the API from your terminal. This helper function will parse the data that's coming to it. So in this case, it's a sequence of words. And then when you send data as curl or through your shell command curl, Julia actually receives them as an array of uint8. So then you'll have to transform them to proper strings using the string method, and then we encode them. And after that, once that is done, you can start to sample from the model. So whatever data that you get, you can pass it to the model, and you can get one word, which is the word that the model predicts will follow the sequence of words. Then I'm actually sampling 3 words over here. So let's say, then you can keep appending the new words to the existing context. Because the memory size is fixed, you will have to drop one word from the beginning. So I append one word, I also drop one word from the beginning. And then this function returns the final result. So Mux has this really handy macro at app that spins up a server on the fly. So over here, the way I have defined is, this is going to my API endpoint, and this is my lambda function which passes the the input to my helper function. So Julia receives the data from your curl call as a dict, and the actual data will be contained in your inside the data keyword, and then you can launch the API with this serve method. So I have actually done all that over here. So over here I have loaded the train model. So I have also created the vocabulary dictionary and all. And then I have created the initial input query. And this is the helper function we talked about. And I have imported mux over here. So this is where we spin up the server and serve the API and all. So we'll just see if what we get. Uh, the sequence of words is from the pen tree bank dataset, which I used to train the model. So you can use this data flag to pass a sequence of words to it. And this is hosted on localhost, and by default, Mux hosts your API on port 8000. And like we defined, this will be your API endpoint, which we have um, um, yeah, over here. So we can make a call to that. So the initial input was it entered at what the worst possibility would be, and the model predicted in worst possibility would be, and then words irresponsible said it could be someone over here. So when you parse the data set, you remove a lot of unknown or rarely occurring words. So yeah, so this is the entire workflow. I'll just go back to my presentation. Yeah, so like I said, you can use Mux or HTTP or Genie.jl, and yeah, we talked about all this. And I just want to highlight uh, two things I really like about Flux compared to, let's say, TensorFlow and PyTorch. So this was an issue that was raised on the Flux repo, that they need an embedding layer. But like I've showed you, you don't actually need extra layers or anything, because you can use Julia primitives themselves. So if you come from a TensorFlow or a PyTorch background, they are where you can't really interweave other packages or the base library primitives into it. But inside the Flux, data structures are available to you. And also it's really easy to access the internals of Flux. So we looked at how we can uh, clip gradients. We can access the gradients and then manipulate them to clip them. And I think as a next step, I would really encourage you to look at transformers.jl, which is an implementation of the transformer model. So over here, for pedagogical reasons, I chose to use loops instead of batch processing. So uh, uh, that is not really going to be fast on GPUs. So if you check out transformers.jl, you can see that they have made good use of Julia's packages QArrays to train models on GPUs. Yeah, so yeah, that's it. Oh, yeah, Sushil. So if you guys have any questions, you can post it in the chat over here. So yeah, the data said it's Penry Bank, and the code, yeah. So someone has posted the code to, uh, yeah, from my repo. So that doesn't have the deployment part. I'll also share it. And yeah, so those two are actually the same person. It's my repos. And the alternatives to mux.jl.
So that brings us to the end of today's discussion. Uh, Anyone, if you have questions, keep putting it in here in the chat box, or you can unmute yourself and ask the question. We still have some time for Q&A. Deepak, there's a question here in the chat box. It says, how does the performance of this architecture compare to its version in Torch or TensorFlow?
Yeah, so over here I haven't, my priority wasn't really performance over here. Like I said, for so that you can easily follow the way the model works, I have defined whiles and loops over here. But you can get the same performance as PyTorch in Flux as well if you batch it and uh, train it on GPU. So, like I said before, when it comes to using Flux, uh, it makes all Julia methods and all Julia libraries also available to you, in the sense that you can mix things up. For instance, if you are training something in TensorFlow, and inside your TF graph, if you want to use, let's say a CV2 image reading method, it's not really going to fit well. It's not going to mix well with the TF graph. Or let's say if you want to use a differential equations package inside your TensorFlow graph. So those things are going to be really hard if you're going to do it in Python. On the other hand, with Julia, you can mix any package that you want and things will work really well. That composability is one thing that stands out. And also it's really expressive. So if you look at Flux implementations, you'll see that it's almost the same as the pseudocode. There are no bells and whistles that you need to add to make it run. Yes, I have tokenized this data set. So pre-processing, I think there is a package called uh, I can't recall. If you leave your email ID with Sushil, I can point you to the pre-processing packages.
Sure, I'll ping my email here any further question or any interest in any of our offerings, anyone can always reach out to me, and I'll be happy to get the right answer.
Yeah, Zygote actually helps you calculate the gradients. Yeah. How long did it take to implement? I don't recall. I actually did it bit by bit over a couple of days, so I don't know. So if you need help with running uh, any of this on your own, like reach out to Sushil and I'll help you out. Can you talk more on Zygote? Yeah, you can write your own custom grading methods in Zygote. Uh, on Zygote, I would really encourage you to go to the Zygote Julia page and just skim through the documentation. It's really interesting over there.
Any other last minute questions? If not, yeah.
Uh, I'm not really sure about that, but the transformer.jl was actually a GSOC work. So there could be similar stuff available. I'm not really sure. Julia Pro, yeah, you can use it as an IDE. It's built on top of Atom. Atom is the IDE that I was using when I gave you the demo. I mean, the editor that I was using. Yeah. So yes, Julia Pro is an IDE. Yeah, NLP is used in chatbots. So even when you are doing, when you're typing messages out, so you will have suggestions, right? Uh, when you type a bunch of words, and then your message app might give you suggestions. So those are language models over there.
All right. I think. Go ahead. There's another question. Keep going.
No, there is bidirectional transformers. There has been a lot of progress, but do check out transformers.jl. That has the transformer implementation as well as bidirectional implementations. Yeah, you can use BERT through transformers.jl. So it gives you pre-trained models over there, so you don't have to spend time training it. Mm. To load word embeddings. Uh, so yeah, but what format are you talking about? Uh, I need a bit more details over there. Yeah, so even with glove, I haven't tried it out, but it should be possible. So if it's available as if it's in some way you can read it as an array, then you can, yeah, use those word embeddings. There is also a glove interface to Julia. We can check this one out. Uh, yes, pre-trained embeddings can be saved in any format. It should be searched by model. I didn't really understand what you meant by it should be searched by model. Searched by what model? Mm, the resources for NLP. Yeah, if you can leave your email with Sushila, I will send you some resources for NLP and stuff. Yeah, pre-trained embeddings. I don't know if you're talking about glove or so. I think we had posted two links to two packages over here, so you can use those. Or if you want to train your own embeddings and then save them, you can use Bison or JLD to other serializations. Uh, if there are no more questions at this point, okay, what is data flow? No, I don't think you can run it on AMD graphics card at this point. Sorry.
All right, I don't see any further questions, so I think we can call it a day. In case you come across any other question post this presentation, you can always email us, and we'll be happy to get back to you with the right answer and explanation. Uh, Thank you, Deepak. Thank you, all the attendees. When it comes to offerings by Julia Computing, if you're using Julia professionally within your organization for any of the projects, if you are planning to leverage or you are leveraging already, feel free to reach out to us. You can write to sales@juliacomputing.com, or you can directly write to me. My email sushil.kumar@juliacomputing.com. I pinged already in the chat box. So if you want to know more about any of our product, if you have questions about our support or training offerings or consulting engagement, if you're seeking help, with your current work on Julia, we are happy to help you. So we'll be happy to hear back from you. Look forward to be in touch. Thank you, everyone. Have a good rest of your day ahead.
Yeah, thanks everyone. Thanks, Sushil. Bye.